So being a pilot has plenty of ups and downs, but one advantage we have in corporate aviation is that the aircraft we fly generally cruise at higher altitudes than the airlines will ever use. The Bombardier Global Express can reach 51,000 feet, but more typically we operate between 43 to 47,000 feet. Because airliners don't get that high, the airspace is relatively empty, especially if you are crossing the Pacific Ocean at night, as I did last night. This provides us with more freedom to divert around bad weather or to make observations that confirm the Earth cannot be flat. As you will see in the following footage, we were able to fly directly towards the moon, and its position in the head-up display proves it was below eye level as it was setting. So what you're looking at here is a photograph taken through the head-up display while the moon was still quite high in the sky. And I'll briefly explain the symbology, as that will help you understand the following footage. Starting at the top, this is the angle of bank indicator with marks at 10, 20 and 30 degrees. To the right of that, you see the words EVS on, and that means the enhanced vision system is turned on, and that allows us to see the horizon in front of us. With the EVS off, the background would be completely black, and you'll see that in the following footage too. Below that we have the current Autopilot operating modes. You can see Autopilot 2 is engaged, and it is in speed, LNAV and altitude mode. Speed means the auto throttles will be adjusting constantly to maintain this set speed of Mach 0.85. That is 85% of the speed of sound. LNAV means lateral nav, and that means the autopilot is also maintaining the course across the ground. And altitude means it is maintaining the preset altitude of 43,000 feet. What we see next is this line running from right to left across the HUD. That is called the horizon line, and it represents the position of true level. As you can see, at this altitude of 43,000 feet, the Earth's horizon is below true level. Now this double circle represents the flight path vector and the command being issued by the flight director. The inner circle will show what the flight director is commanding, and the outer circle with the two horizontal wings and the vertical lines represents what the aircraft is doing. When the aircraft is maintaining a level flight, when it is not changing altitude, this flight path vector will be perfectly in line with the horizon line. And what you'll notice when I'm turning the aircraft are numbers moving left and right along this horizon line. Those represent the direction in degrees magnetic. As you can just see here, the numbers 24 represent 240 degrees magnetic. This small symbol that looks like a W is the pitch attitude of the aircraft. And the difference between the pitch attitude of the aircraft and the flight path vector will give us an indication of the angle of attack on the wing. If the aircraft was flying slower, or if it was heavier with a greater fuel load, we will have a bigger split between the attitude of the aircraft and the flight path vector. And that is because we need angle of attack on the wing to generate the required lift. So that's enough theory. Let's get to the good part. Because we are in the northern hemisphere, as the moon was setting, it was moving to the right. And also, because we are flying a great circle route, later in the flight, our heading is less than 240 degrees. So you'll see this 240 to the right of the flight path vector. And this is part of the video I will play shortly. But as you can see, the moon is now to the right of the head-up display. So I had to actually turn the aircraft to the right to put the moon directly in the center here. And what you will notice is that the mode goes from LNAV to heading. That was a manual selection that I made, and it now allows me to control manually the heading of the aircraft. This is the heading bug, and as I change that, you can see it's moving to the right. The flight director is commanding a right turn and the flight path vector is following this command. So that'll all make sense now as you watch the video. And because we are operating in oceanic controlled airspace, we can't just turn left and right at will. We have to ask for permission from air traffic control. And I did that using the CPDLC system with this request. Request 15 miles right due to weather. And that was sent at 0540 Zulu. And just a minute later, they came back with cleared to deviate up to 15 miles right. So they gave us permission for the turns you're about to see. And remember, as you watch this video, this line represents true level. So if the moon is below true level, it is not circling above a flat Earth. In fact, if the moon is below true level, that means it has not set, and that means the horizon is also below true level. So please enjoy. So there you have confirmation once again that the horizon did not rise to eye level and the moon itself was below eye level as it was setting. So it is clearly not moving in a circle above a flat Earth. Now the last part, I'm just going to show you how useful the head-up display with the EVS can be at night when you're going across the equator with thunderstorms all around. Here we can see the EVS is on, and you can see the silhouette of these thunderstorms below us. Now if I turn the EVS off, you see nothing. All you have is darkness. When you turn the EVS on, you can see the thunderstorms. And what I also did was tilt the weather radar down to see those same thunderstorms. I had to tilt it down to minus 9.5 degrees, but you can see the radar painting the same thunderstorms we can see in the head-up display. Now operating without EVS, you really have no idea of what's out there except for what the weather radar is showing you. As you can see, the EVS gives you very good situational awareness.
Shit. High islands?
No, that's way below us. They're clouds. They're clouds way below us.
Oh.
See the tilt's 9 degrees.
-9.
Yeah.